Okay, I usually start with this presentation so that you know me better. This is a very personal presentation, and hopefully the most important question is why you are here, right? Taking physics class. Unless you are in physics department, otherwise you always have that at the background, right? Why I'm taking this physics class when I'm a biologist, right? So I will hopefully answer that question with a personal thoughts. These are not universal. These are not like Coulomb's law. So once this presentation is done, then it's the universally accepted laws of nature. But this presentation is a bit personal. So I graduated from Hacettepe University, nuclear engineering. Then I switched here to material science and nanotechnology department at Bilkent. This building was not there yet, but I was a student in it. Okay, so then I finished my master's and PhD, and I went to this beautiful city, San Sebastian, to do my postdoc. Then I came back here as a professor. So I want to start with a very core idea. Let me just shrink this video a little bit. The idea of truth beauty. Okay? Truth is easier to define. Truth is whatever is true, like 1 + 1 is 2. Beauty is a bit more aesthetic and subjective thing, but it's about patterns. It's about some sort of order and a little bit of disorder on top of it, and we find things beautiful. So let me start with a very abstract idea. Let's say you were wandering around and you found a line, right? It's beautiful, it's true, and it's beautiful. It represents some sort of order. Very abstract ideas. Then you know where to look, and you find lines, similar lines, aligned in the same direction in other places. This thing starts going towards universality. But then you find an exception, a line that is not pointing that way. This is very abstract, okay? Then you now know that there is an exception. You are wondering whether there is only one exception or there are multiple exceptions. So you find other lines because you know where you are supposed to look. Then maybe you find another exception. Then you start realizing there are pentagons all around, okay? Now you know to look for pentagons. You keep searching. So you are filling in the gaps of truth. And it's a beautiful process, okay? Then eventually you make all the picture, you bring all the picture together, and you realize that it's actually simpler than what you thought. But you were looking in 2 dimensions. You just go to 3 dimensions, and it's a simple dodecahedron, and you were finding every corner because you were looking in 2D. And even things that are very far away come together, maybe. Maybe. It's an abstract idea of scientific discovery and also the meaning that you get from your life. It only manifests itself when you look backwards. You look backwards and you say, okay, I did this because I was like this. I am here today because of this, and it all makes sense. Okay? So, scientifically, actually, we are going to, this whole semester will be this kind of discovery, because before Maxwell, these are our electromagnetism equations, okay? There's Gauss's law, Faraday's law. None of them is actually Maxwell's law, okay? But Maxwell realized something about this system. After Maxwell, so this is the Maxwell's term. This is Maxwell's contribution to Maxwell's equations. But it was such a huge contribution that we now call all of them Maxwell's equations. You see? What is the contribution? The contribution is that the equations become more symmetric. This one tells you that magnetic field, change in magnetic field creates electric field. But this one doesn't tell you anything interesting. But once you have, well, not anything interesting, it's still interesting. But this one is even more interesting because it tells you that also change in the electric field creates magnetic field, right? So now the symmetry is completed. Change in one creates the other. And since it created the other, it changed the other, and it creates itself again, right? So it becomes this feedback loop. And electricity and magnetism are tied together. What comes out is the spoiler of this series. It's the season finale. And in the season finale, we will see that electricity and magnetism are two sides of the one coin, and that coin is light. And we are going to discover that light is an electromagnetic wave. Okay, good? You know where it is going now. All right, another example. Here's how we saw the world before Darwin. Just cute animals, no relationship to each other and no relationship to us. Just some sort of servants, or we are walking in the zoo and we are looking at them. After Darwin, it's a story of origins of life, and we are all related, and it's a beautiful and true story. All right. Do you have any questions so far? Okay, truth, beauty, I hope it makes sense, right? Now, I will give you two more concepts, and hopefully we will build a picture of truth and beauty together, whole picture, big picture. Good. First idea is computational universe. So let me just run this. I want to give you two examples, one from John von Neumann and the other one is from Turing. These two people are maybe can be called fathers of computing or fathers of computers, okay? So von Neumann, for example, was interested in many things, from Byzantine history to quantum mechanics, and he was the best in all of them. He also introduced game theory, which is now a very important subject in economics. He was also thinking about self-replication. Why he was thinking about self-replication, it's a long story. Should I tell you? Yes? Okay, very quickly. So the idea is that you go to Mars, and the Mars is red, right? Because of iron oxide. So you send a machine that is made up of iron. It takes the iron ore, okay? It separates oxygen, puts it in the atmosphere, and uses this iron to make another copy of itself, okay? So that you send one machine, it makes 2,000, 3,000, millions, billions, and in the meantime, it creates oxygen for you. When you arrive, it's a nice oxygenated planet. Very good idea. But then he said, okay, how a machine can make a copy of itself, okay? So he started analyzing this in his head because there was no computer. And what he discovered was basically an abstract mechanism of DNA replication. DNA was not there yet, okay? But he already, just that thought process of how a machine can replicate itself leaded to the mechanisms of DNA replication, okay? And any kind of replication, okay? How about Turing? He was also a mathematician, and he started wondering why there are these patterns on the animals, like stripes or benek. What do you call benek? Let me call it spots or stripes, that kind of stuff. And he described it with a reaction diffusion system, some sort of mathematics. And he predicted that there should be two kinds of chemicals, which he named morphogens, that should be able to produce these patterns. And those morphogens were found after 30 years. Okay? So, let me keep going. Are you bored? Are you sure? Do you have any questions? No? Let me go even more, abstract. This is a work done by Stephen Wolfram. So he was playing around. His idea is there is a real universe here, and then there's a computational universe down there, okay, an abstract universe. And he is a creator of Mathematica. Have you heard of that software? It's a very symbolic language. It's very nice in taking integrals and stuff like that. You must have heard of Wolfram Alpha. Yes? Okay. So all of them are due to Wolfram. And he sees computers as telescopes. Just like with telescopes, you explore this universe. He's exploring, using Mathematica, the computational universe. And one of his explorations is this Rule 30. My camera is blocking it, but it's named Rule 30. So what is Rule 30? It's a very simple game. So you basically look at the rules and you decide what to do next. So these are all zeros and this is 1. So I have 0, 1, 1. I go here and I find 0, 1, 1. 0, 1, 0. So 0, 1, 0 is here, and it tells me that the next cell should be 1. Okay? You continue playing this game, and it's a very simple game. But what happens is that you get this thing that you cannot explain with any kinds of mathematics. You can't zip this function. You cannot find what's going to happen here unless you actually play this game. There is no shortcut. So simple, very, very simple system led to very, very complicated dynamics, right? So my message here is that computational universe is already very, very rich, okay? Let me give you another example. Before that, let me give you this. So Wolfram is nowadays trying to actually derive physics starting from computation with no assumptions. So he's playing these games and he's trying to find systems that would correspond to our universe, systems that would have gravity in it, systems that would have quantum mechanics in it, okay? Very, very highly speculative endeavor, but it's very worthwhile, in my personal opinion. Here's another beast in the computational universe. Do you know what this is?
Those spots, they are periodic. Like
Yeah.
if you give one number, you will get one number, and then it will repeat periodically.
Very nice.
There's a Veritasium video about it.
Exactly. Very nice. Thank God we have Veritasium, right? Exactly. So this is Mandelbrot set. It's purely mathematical object. Does it already look nice? It does, right? It's basically a very simple function in complex plane. By complex, it's not complex. It's very simple, really. But as you mentioned, these darker places correspond to convergent series and the brighter ones to divergence. It's an absolute beauty. It's bounded. Smaller patterns are embedded in larger ones, and it goes on forever. Let me show you. So we are zooming in to the Mandelbrot set. It has its own copies. And that's a very important property of these systems, that they have their own copies. We are going to see another copy deep down there. There it is. Do you see? And it goes on forever. Okay? I can give a whole course about self-reference, self-similarity, having yourself inside yourself somehow. And we see this in many systems. The message is there's a computational universe. It's very rich, and somehow it describes our universe. Okay? Now, are you bored? Are you sure? Okay? Good. Now let me talk about emergence. Emergence is not a very hard concept to grasp. Think about a bicycle. You have bicycle parts, and you connect them in a certain way. Do you still have bicycle parts? Yes, you do. But you have another thing. What do you have? You have a bicycle. Okay? What's your name? Tuna. Tuna is composed of chemicals. Take them apart, they are chemicals. Bring them together in a certain way, you get those chemicals plus tuna. Okay, it's emergent. You have very, very rich, very, very interesting thing when things come together in a certain way. So that's called emergence. So let's use these two concepts. And I will start with a speculation that computational universe plus emergence gives birth to physics as we know it. So physics, deep down, is mathematics. That's why everything mathematical works here. Like there is this famous piece about unreasonable effectiveness of mathematics in natural sciences. Okay? And I believe that this is the reason, because if you go deep down, our real universe is supported with that abstract computational universe. But it's a speculation, okay? But after physics, we don't need any speculation. We definitely know that chemistry emerged from physics. You know how you have been taught s, p, d orbitals, right? They all come from solving Schrödinger's equation for hydrogen atom. And you get your orbitals, okay? Purely mathematical thing gives rise to chemistry, right? Then chemistry, what emerges on top of chemistry is biology. On top of biology, you have psychology. Psychologies come together and create civilizations, and civilizations make art. That's the whole picture that I promised you. And it's a personal picture, okay? You can make it different. You can unzip civilization and put all the economics, social sciences, things like that there, but it looks nice this way. So, biology is very interesting in these emergent levels. Something really interesting happens. It's significantly different from chemistry, right? So, why is that? Again, my personal opinion is because of this backwards arrow. Biology is the level where the level can control its building blocks. Chemistry cannot change its building blocks because it's very tightly bound together. Are you bored? No? Are you sure? Are you sure? So, chemistry is about nucleus. You have carbon nucleus, and it can't change to nitrogen. It can only change if you have a nuclear reaction. That rarely happens at these temperatures. You have to be in the middle of a star, right? And middle of the star is also very interesting in terms of chemistry. But in our temperatures, biology is very interesting, and it's because it can change its chemistry. Just cells signaling each other. What are you going to do today? I don't know. I'm going to become a fingernail cell. Okay, I guess you have to get some keratin for yourself, right? And they just signal each other. They realize what they are supposed to do, and they do it. They change their own chemistry, right? You are doing it every day. Okay, psychology can change your biology. Civilization affects your psychology significantly, although you are the ones who made that civilization, right? And art contributes back to civilization. You can think of it as a tree, and these parts are really murky. We don't know what's going on there. Maybe there are another kind of branching down there. But once it comes out of the ground, it's a single throw, and it starts with physics. Physical constants are same everywhere. It's a very nice start. The rules are the same everywhere, and we understand them very, very, very well. Okay. So let me make one of the points here. Do you see that no matter where you are going to end up, at which level you are going to contribute to society, there is a path that goes through physics, right? You can still do biology without knowing physics, really. You can still do it. Why? Because once you are on top of a bicycle, you don't care about the parts. Unless when they are broken. Then you say, I wish I knew what these parts were meant to do, how they were meant. And then you go to some place where they repair shop, and they repair your bicycle because they know the parts. So if you want to fix the biology, if you want to create a vaccine, you can't do it without knowing any physics, right? But you can still do biology at that level. Do you have a headache? Here is aspirin. But you can't do breakthroughs. You can't create aspirin in the first place without knowing physics, chemistry, etc. All right, that's why we are teaching you physics, but I will come back to this. That's also how your brain works. Let me give you an example. You take your data from retina, and there is this place that just analyzes it and sends it up. But once it hits V1 down here, V1 takes information from top levels, also from the bottom levels, and it synthesizes it, sending it back and forth. So let me show you what happens next. So I'm going to show you 5 shapes. Ready? 1, 2, 3, 4, 5. Do you see the pattern? You are not supposed to see it. Now I'm going to tell you, you saw that the white parts, there is something written there. In the white parts, not in the blue parts. I was tricking your upper hierarchy. Can you read lift? Very good. So, of course, there are other arrows here too. Like, for example, what you have in the computational universe actually decides why you mostly use 12 notes in the Western music, right? Not 11, not 13, 12. There's a very, very good reason, mathematical reason for that, right? And you can alter your psychology with chemistry directly, right? So it's a web. Let me ask you, are we a bag of chemicals? Maybe yes, maybe not. Well, this presentation says that we are not. We are bags of chemicals, and that makes all the difference, okay? Because you can't just put chemicals in one bag and shake it and get tuna. It has to be bag inside a bag, inside a bag, inside a bag, some sort of organization, because these bags make sure that improbable events happen. For example, digestion. There's some food lying around, and you want to digest it. What do you need? A very low pH. But very low pH will break yourself too, right? So what do? You keep them in lysosomes, those very low pH. You take in food, you fuse together with lysosomes, you break down food, and you are good to go. You see? So the bags control, that's how biology controls its chemistry. And the looseness of bags tells you why it happens at biology, because once you are at biology, you have an excellent permeability of bags. You can take in, take out anything you want, but carbon atom cannot take in protons, neutrons as it wishes, right? So it's a tighter bag, that's why it doesn't have this backwards loop. Does it make sense? All right. One other message here is that this is the time for you to actually go ahead and read the textbooks of these levels. These levels are not only the levels of reality organizational levels of reality. But there are also textbooks for them. You have chemistry textbook, you have physics textbook, you have biology textbook, psychology textbook, and lots of textbooks on civilizations. You don't really have an art textbook. So for art, you should just, whatever you like, music, painting, something, right? There must be something that you like. Solving Rubik cubes really, really fast. That's in the art level, I guess. So having some sort of connection to art is also nice. So the most important message today is for you, before you grow older like me, read these textbooks, not for the grades, just from the first page to the last page, looking at the authors, what they did, every line, and you will thank me later. Okay? Good. Let me get at least one question. Let me force you to give me one question, because I don't want this to be a monologue. Any questions? Yes?
Does that mean we can't understand or do physics without knowing computer universe?
So there is this 80-20 thing going on here. Do you know that thing? That you just need to know 20% of something to get the 80% of the benefit. Okay? So we are not actually teaching you all mathematics. We are only teaching you, I think, 1% of it, and that's calculus. And even that is too much. You don't need all the calculus to be good at physics. You only need to know a few integrals. That's all. Okay? Once you know a few integrals, and you can always learn as you go. And if you are wondering personally for yourself, make no mistake, be sure that you already know all the mathematics you need to know. Like, do you know sines and cosines? Yes, you do. Do you know how to integrate them? Yes, you do. So you know everything.
Also, why math isn't in this?
It's math. It's
Computer isn't.
computational universe, mathematical universe, whatever you want to call it. That abstract place where you don't have matter, you just have logic, formal systems, just ideas that lead to other ideas, that lead to other ideas, right? Any other questions?